name is Jakub Dżon. I've been developing software for different industries for almost a little over 10 years. The most recently, I've been working in Codewise, a company that delivers software for ad tech. I've been leading development of our DSP platform called Volume DSP. And today, I would like to tell you how we've built the software, what decisions we've made along the way, what implementation decisions were made, what kind of changes we decided to make along the way as well. For us to understand each other and for me to be able to comfortably refer to certain concepts coming from ad tech, I would like to introduce some vocabulary that's common in ad tech. How many of you are familiar with ad technology? That's good. That's really good. Let's start with DSP. DSP is demand-side platform, which is a service or system that's responsible for buying ad space on behalf of its customers, which are advertisers. SSP, on the other hand, is a supply-side platform, which is a system that's responsible for selling ad space on behalf of publishers. So these are kind of opposite sides of the trading. Ad exchange is the middleman here between DSPs and SSPs, which is responsible for running auctions on ad space, which are created mostly by SSPs. QPS, it's technical term, which is queries per second. It's used to describe how many bid requests are sent or can be handled by systems in ad tech. A creative, that's a common name for different types of ads that can be displayed over the internet. For example, banners, rich media banners, video, audio, and so on. An impression is an event that describes showing the ad, the creative, to end user. And before we get into more technical look at our system, I will show you how the whole process of showing ad looks like. So when the end user on the left-hand side opens an app or site on his device, which is not only mobile but also desktop, the request is made to an SSP by that site or app, describing the device that it will be displayed on. So IP address, device ID, user agent, and so on. Then SSP is integrated with one or more ad exchanges, and it sends the request in parallel to ad exchanges describing the requirements regarding the creative that would be displayed. The ad exchanges in turn are integrated with one or more DSPs, and in many cases, different ad exchanges integrate with the same DSPs. Ad exchanges create auction and send bid requests to DSPs, describing the same what was received from SSPs to DSPs. It is pretty simple diagram what's happening, because there are some cases when ad exchanges transfer the same bid request to the other ad exchanges, and as I mentioned, same DSPs are integrated with many ad exchanges, and also app or site can be integrated with more than one SSP. So we can see a lot of duplication at the end as well. And I would like to talk about requirements we set for ourselves before starting working on our product. We knew from experience that the traffic that comes into ad tech services fluctuates throughout the day. So sometimes it's over 100,000 queries per second, sometimes it's 50. So it was crucial that our application is scalable, and not only scalable, but auto-scalable, without over-provisioning, because it might be costly to run many servers to handle the peak traffic on the low hours. We wanted to be sure that even if the world is on fire and parts of the network are down, or our services are down, we're still working, we're still operating. Hence, we wanted to have as high fault tolerance as possible. Because we would be running millions of dollars of ad trades throughout our system, we wanted to be safe on the data side. We wanted to keep all the records, they couldn't be lost. And we wanted to be sure that we were able to bill our customers and be sure that we can verify what the ad exchange bill us for the ads that come from us. We wanted our system as well to be maintainable as possible, because we knew that it would grow really big and we would introduce many changes throughout its whole life. We would make a lot of deploys, hence the maintainability. Because of the requirements regarding the safety, we had to introduce observability to the system. We wanted to see what's happening on the technical side and business-wise, whether we are okay with the numbers that we would present to all the sides of the trades. Because there was such risk of having a bug in the system, the bugs would be really costly. And mainly because it's really good to deliver high-quality software, we wanted to be able to deliver that. So, the stability. The other thing is that our system won't be able to work without integration with other systems, with other exchanges. And we expected to integrate tens of them within months. So we wanted to be able to introduce them into our system very easily, without any deploys, redeploys, whatever. I've shown you the traffic profile before. That was the actual profile, recent profile of our system. So around 150,000 queries per second. And we wanted to be able to handle even more. So hence the throughput should be as high as possible. And latency, we've checked integration documents from our other exchanges that we wanted to integrate with. And the maximum latency that within which we should be able to respond was 150 milliseconds. So that's the hard requirement here. Having in mind that, so all requirements, let me run you through the architecture, initial architecture, the changes, and the final, most current architecture of the system. So looking from high level on the system, you can see that. So we integrate with a few different separate blocks. We have the other exchanges that send us traffic through load balancer. There is our system volume DSP, which in turn uses our other product, volume tracking, for storing all impression information. We use S3 for storing creatives, and then we use CDN to deliver those creatives to the audience. That's fairly simple, but let's put a few more pieces here. That's what it looked at the beginning. That's how we've built it. The blue elements, that's the latency critical path, those 150 milliseconds. And at Exchange load balancer, they're pretty obvious, but then we have our edge servers, traffics. These are basically HTTP servers that receive OpenRTB requests. OpenRTB is a standard for describing ad space or requirements regarding ad creatives. and sent in JSON in our case. So the responsibility of traffic is to decode the JSON, transform it to our own format, getting from the incoming messages everything we need, no more, no less, to conserve the network. Then we have bidders, which are servers responsible for matching incoming traffic, incoming requests to campaigns created by our clients. So the campaigns have specific parameters describing where they should be displayed, for whom, and we match the data from bid request to campaign to creatives that are defined there. Also, there is plenty more logic there regarding matching, excluding certain traffic, including specific one. And we've got integration with bidding helpers, which is around 4 or 5 separate services reachable over network. Well, all arrows are network calls. So, which are responsible for very special cases which wouldn't be right to be in bidders. All the services that are down from traffics are discoverable through Eureka. We don't use any load balancers between the servers. We use plain TCP binary communication in our own homegrown format. We've got servers, client-side load balancing, thanks to Eureka Service Discovery. And that's basically it about the critical path. We've got several more services that are very important for processing the whole traffic. So we've got a processor down here, which is responsible for recording information about creatives that were actually displayed, about impressions, which we receive also from ad exchanges through load balancer, through traffic. So there are 2 endpoints in traffic in this picture. The win notifications are sent from traffics, through Kafka, then through processor. From processor, they are sent to our proprietary database, VolumeDB, and Redis is also used for the duplication of messages in case of some kind of reprocessing or in regular work as well. Zookeeper, that's the dependency from Kafka. And we've got budget service on the right-hand side, which is responsible for recording the spend for the client or per campaign to do the actual billing. And the information to budget are sent again through Kafka from processor over there. And yeah, I didn't put many more services there that are kind of external from DSP, but their purposes is accounting and so on. What else we have here on the diagram? There is campaign management, which is simple service for providing information about campaigns, managing the campaigns. We've got creative management service, which is responsible for managing creatives, for putting them in S3 and providing information about them to bidders. Then there is the rest is like in the previous diagram, S3, CD, and then end user. That's the display of an ad. There is Cassandra used for persistent replicated storage for campaigns and creative management. So right at the beginning of our work, or before we started coding the actual business logic, we had to make a few important decisions, like how to parse JSON. Because we're latency bound, we had to conserve time, CPU time, everywhere we can. So we've done initial research on parsers. We started with Boon because it looked very promising. But we found a bug in it that wouldn't allow us to use it. And we didn't want to wait for fixing it ourselves. So we moved to Jackson, that data bind. and JSON streaming. We did the comparison to see which one would be better, because working with data bind would be much easier, less work. Streaming we expected would perform better, but we didn't know the difference. So that's how it looked. Data bind, we are able to parse 3,600 queries per second of incoming requests, and with streaming 7,900 QPS. So we decided to go with streaming and implement all the cases that are interesting for us in the code. So we could exclude all the pieces we were not interested easily. The other important decision was how to implement the edge service, the traffic. We needed to choose what kind of HTTP engine to use. So we started with servlet containers, and the other option was Netty. We're thinking about Netty because we knew that we will use Netty later on in communication between traffic and bidder. But we started testing Jetty, and that's how it looked at the beginning. With Jetty, after some tuning, we were able to have those 7,900 QPS, because that parsing we've tested with Jetty. And then when we've migrated to Netty, that was 12,000. A moment later, 17. A bit later, 24. Eventually to reach 31,000 QPS on the same hardware, of course, and the same test data. So we're able to tune traffic endpoint to that performance. And the obvious choice after that was Netty. We started working with Netty in traffic servers. Afterwards, while we've developed the rest of the services, there was a lot of other decisions, but these are the main ones. After we've rolled out the service to production, it worked for a while. We decided to make certain decisions. They were not all at the same time, but gradually. First one was Kafka and Zookeeper. We didn't really want to take care of them, maintain 2 clusters of servers for Zookeeper, for Kafka. During the prod running of the application, we faced a few problems. We had to recreate the cluster or fix it a few times. So we've decided to move on to Amazon Kinesis to get rid of the headache of maintaining the 2 clusters and fixing it. We didn't see any issues with Kinesis so far, and it's been running like that for 1.5 years. The other thing that was problematic was the threading model that we've chosen to implement the integrations within the services and between services. So at the beginning, we used multiple threads to handle one request in a service. Especially it was visible in bidders where we were integrating with many other services using different thread pools usually. There were switches between the threads while the request was processed. And we saw in peak times queuing between the thread pools, which were causing ripple effect to traffic, and the latencies were going up. So we've chosen to use one thread to process the one request in a service, including calls to the outside services, handling responses. So using Netty functionalities, we are able to guarantee that one request in one service will be handled always on one thread. We've put circuit breaking on all our integrations between services, and we've used one of the most popular frameworks. Can you guess which one? Yep. Exactly, but it wasn't really comfortable for us using Hystrix at long run. We had trouble tuning it to fit our needs. It was too big for us. So we've basically resigned from Hystrix and we've implemented our own very simple circuit breaker that works fine and gives us what we need. There are other problems or functional requirements that were put in front of us. Like, we had to cache certain things to have access to them between different requests. So we've used Redis, and we had it only in one data center. But the real requirement was to have cross-data center replication. And we couldn't do what we wanted to do with Redis, because we wanted to put as well some logic on top of that cache. So we've chosen Hazelcast, which in hindsight might not have been the best choice, especially having a look at the most recent Jepsen report on Hazelcast. I recommend the read. But we're with Hazelcast. When it's working great. We've implemented our own services within Hazelcast to provide logic that we wanted it to provide. And moving on to the image that I've shown you before, the traffic profile of our system. So we received, that's, I know, from a week ago or 2 weeks ago, we've been having 130,000 transactions per second incoming to our system. But these were only bid requests. And we also receive win notifications, which are very, very different in the traffic is very different in profile. It's only fraction of bid requests, and we're handling them with the same edge service hidden behind the same load balancer. So we've decided to create second endpoint, HTTP endpoint that would be handling win notifications and would ease development of both services and tuning, basically, because if we receive traffic with completely different profiles, with completely different payloads, with different sizes, with different performance requirements. For win notification, we don't have to stick to 150 milliseconds. We can process it much longer. So that's what it's now in our system. We've introduced, well, we've modified processors that were already in the picture by adding netty HTTP endpoint there, hiding it behind dedicated load balancer, and moving away all the logic pertaining to win notification processing from traffics. So now we're pretty much free to tune them separately and adjust to the requirements of incoming traffic. The whole path, blue path, stayed the same, but on the way we've introduced a few more bidding helpers over there, so a few more integrations. On the previous diagram, there was S3 over there, over traffics and bidders, which was called the same business config management. We configure our integration endpoints using JSON files stored on S3. So at the beginning, we didn't put any management on top of that. We basically changed JSON and uploaded it to S3. It worked fine until a few concurrent updates. And we've put a service on top of it. Well, we knew it would happen eventually, that there would be trouble with that, but that was the easiest way to go to start working. We've put a service on top of that that's responsible for managing the file. And it's used by many services, traffics, bidders. Also, I didn't put some more arrows over there because it would obscure the view, but also bidding helpers use that. Processors use that, and other services that's not on the picture use that endpoint. I've put Hazelcast over there on the diagram, and Redis stayed there because one piece of functionality stayed there as well. We didn't want to move it to Hazelcast yet, and it's still working fine with the processor. I've changed Kafka to Kinesis on the diagram down there. of course, got rid of Zookeeper. And that's virtually all the changes I mentioned or didn't mention before. And what about those requirements that I've mentioned at the beginning? The auto-scalability. It's very easy to define auto-scaling rules when you have small services that have single purpose, that have known traffic profile, known payloads that are coming. You can define the rules very easily. So that's checked. And it worked for us really great during peak times. New instances were spun up. When the calm time came, they were shut down without any hiccups, without problems. The fault tolerance. Because we deploy our services in many networks, in many data centers, we're not impacted by death of any of them or being unavailable or other problems. Basically, the other services that are still alive or reachable take over the work. And probably new ones are spun up if the others won't work. So, checked. Safety. Because we use data storage that itself has certain safety guarantees. We have backups in place for the data that's critical. It's also checked. The maintainability. That's also very easy to start working with our system, with developing our services, because they have single purpose or limited scope where they operate. You can learn the code very easily. You can start working on it, fixing it very quickly, and you can roll them out very quickly. It's not uncommon for us to make 5, 10, 15 deploys per day if we need to. So it's also checked. The observability. We've created an application skeleton for our services that has certain health checks built in, has hooks that allow us to implement very specific service-related logic. Services provide metrics on its work, how they perform, the business metrics as well. So we can monitor that, and actually we monitor it with another dedicated service that kind of watches over the whole system and notifies us if anything is out of order. So that's also checked. The stability. In our old services, we've implemented 3 levels of testing: unit integration in isolation only using mocks, and end-to-end testing. All the tests that relate to the actual business logic, to how the system should operate, how it's used by our clients, have been put into end-to-end tests. The integration tests cover the whole surrounding of the system and how it behaves from the perspective of its clients. And unit tests basically cover the code on the lowest level. So thanks to having, again, very limited scope in each of the services, we were able to write all of these test suites very easily and quickly. The next thing is interoperability. I've mentioned the business configuration management service before and the JSON file that we're changing. That was for configuring our endpoints or defining at which endpoints we were able to receive traffic from other exchanges. And integrating new one is simply adding a new entry in that JSON file, and that's it. No redeploys, no restarts, anything. So in a matter of minutes, we can turn on new integration and start processing traffic. And thanks to auto-scaling, we immediately go up and running. So it's checked as well. The throughput. We've proven that we're able to process 160,000 QPS in production in peak times. And the most recently, that's around 130,000 QPS. It's working fine. Within 100 millisecond maximum latency on processing the response from coming to the system and sending out the response. So it's checked as well. I think I'm done. Do you have any questions? Yep.
Because I think you should check this and you show everything clean. But I think that you have a lot of challenges because you still need to face. You could tell more about it?
Okay. So when we integrate with other exchanges, usually all the integrations have certain quirks. So sometimes when we integrate new other exchange, we have to change some code to adjust, but it's not always. It's one time for few integrations that they do something different than the specification defines. So that's one challenge. The other one that we're still fighting with the throughput and latency. We try to lower the latency of our services. We try to deal with, that's a separate thing, we try to deal with Hazelcast, which is annoying, especially replication between data centers of the data that it's storing. What else? It's actually a lot of them, but okay, we can talk after the talk because yeah. Any other questions?
How many data centers do you have, and how do you divide traffic to those data centers? And the third question is, if one data center fails, how do you switch?
Okay, that's a fair question. So the bidding endpoints, the whole blue path is deployed in 2 data centers. We're deployed in Amazon, so we use 2 data centers, one in Europe, one in US. We have separate endpoint URLs because we don't expose one URL to all the other exchanges. Usually other exchanges say that, hey, we have our data center in Europe, do you have Europe endpoint? Yes, there you go. So that's the endpoint in Europe. Same goes for US. So there is no that kind of load balancing between the within one endpoint. But if anything happens to one of the data centers, we just change the DNS, pointing it to the other data center. It can handle all the traffic from the whole world. So that's manual intervention here required. What was the last question?
About this failure.
Okay. Okay. Anyone else? Yeah. Okay, so we're using external service of hosted graphite for creating dashboard for our needs. We use Logly for sending our logs outside, but we limit the logging as much as possible because we rely mostly on metrics. What's happening in the system, we would see quicker in the metrics than in logs. And also because of the amount of metrics we're gathering right now, we will be transferring to our homegrown database for storing that, to have the whole history of metrics. Does it answer your question? Okay, go ahead.
When a new feature is deployed, what needs to be done on the side of logging and metrics so that it is actually considered good enough to go to production?
Okay, so if we introduce integration within the system, that we integrate with other downstream service, for example, because there are two different cases when you integrate with ad exchange and downstream service. When we integrate with downstream service, we automatically have, thanks to our client framework, metrics regarding numbers of requests, numbers of errors, numbers of the timeouts, the latencies on integration. That's a must, and that's out of the box using our own integration framework. And while we're integrating with ad exchange, so the traffic that's coming to us is introduced As well, we have out-of-the-box monitoring on number of requests, the times when we respond with no bit, the times we respond with no bit because there was an error, or the actual money that we bid on the request. So integration-wise, that's what's there. Logging, we don't care about logging really. So there are no musts. Yeah. Okay, so we're using Java 8. Recently, a few services were migrated to Java 9. The services are packaged within Docker containers. They're deployed. On our boxes, we don't have any service collocation, so it's kind of one container per one VM. And you've asked about GC poses. I don't know. I don't remember. I would have to check the logs. But yeah, that's what we've got. GC logs everywhere as well. So, anybody else? Okay. Thank you.